In this video, I will go over the homework that follows the lecture 7.1 on calculus with inverse functions. So the main objective here is to understand how the relation between the function and its inverse affects or creates a relation between the derivatives of such two functions. And as always, I hope you watched the lecture, as I will be, as I'm doing the homework, referencing certain things from the lecture, assuming that you have watched it. So let's go ahead and jump right into it. The first problem is to find the equation of the tangent line for a graph find the equation of the tangent line to the inverse at the point for, okay, so we need to really understand what's going on here, right? So this is a function. So here's my function. The function may have an inverse. So here's will be the inverse of that function. And the question is asking me to find the equation of the tangent line to the point somewhere on the graph of the inverse function, but it's the equation of the original function that is given. So to find the equation of the tangent line, we're going to use the point slope formula. In this case, my point is given to me explicitly as -1, 0, and the slope is the derivative, but it's the derivative of the inverse function evaluated at x equals -1, right? So we know pretty much all the ingredients except this one. How do you find the derivative of the inverse function? Well, one way will be to actually find the inverse function, but in this case it will be impossible to isolate y once you do the first step of swapping x and y. It will be impossible to isolate y. So we just cannot do that. So what do we do instead? Well, instead we're going to use the relation that says that the derivative of an inverse function is the reciprocal of the derivative of the original function at the corresponding point. So the derivative of this function evaluated at x equals -1 is the reciprocal of the derivative of the original function, but evaluated at the corresponding point. And the corresponding point here, what is the corresponding point to -1, 0? Well, -1, 0 on the inverse function corresponds to the point 0, -1 of the original function. So we're going to be evaluating this derivative at 0. And this is relatively easy. Now, to find the derivative of the original function, we just simply differentiate it using the rules of differentiation. I'm still going to write every single step. So here we have -25x to the 4 minus 5x minus, well, nothing. And evaluating it at 0 gives us -5. And now we can put everything together, right? So we have all the ingredients. So the equation of the line will be y minus 0 equals, so the slope is going to be 1 over -5. So it's going to be -1 over 5 x minus -1. So the final answer is y equals -1/5 x minus 1/5. And before I input this, I just want to show you how what we've done actually makes sense, right? We can check our work in Desmos easily. So we can graph this equation, y equals -5x to the 5 minus 5x minus 1. We're looking at the point 0, -1. That corresponds to this point, right? Now, the inverse function will look like this. We're just not going to be able to write it explicitly. So the point on the inverse function at which we're looking for the tangent line is the purple one. It's right here, right? And we found it to be, and we can actually plug it in and see if it works. We found the equation line. We assume it's this. And it totally looks like it, right? So we are pretty sure that that's the right answer. So let's type it up. Now, if you want to take advantage of technology in problems like this, you can definitely type something like this: the reciprocal of the derivative of the function evaluated at 0. And I thought it will give you the answer, actually. I never defined the function, right? So we have... Interesting. So in order for me to take advantage of this, I need to actually redefine a function. And now once I created a function, I can type things like this. And that's -1/5, right? So that will be a little faster than doing it by hand. Anyway, let's continue. We have a similar problem, so except this time, what are we asking? Graph the tangent line to... this time we have to graph it. So let me write down the function. To graph it, we have a point right at -3, -1. And basically, to graph this function, to find the equation, we're going to use this point slope formula. And we happen to know the point. We don't know the slope yet. To find the slope, we're going to use this fact. And now, to actually find this, we're going to find the derivative of f, which is 6x squared minus 3. And to evaluate this at -1, this is what we get. So the slope is 1/3. So the equation that we have to graph is y minus -1 is equal to 1/3 x minus -3. And now, basically, to graph this, we have to find the point -1, -3, -1. So it's going to be the point right over here. And now we have to graph the line with the slope 1/3. So we go up 1 over 3. So that's going to be the equation. Not the equation, but the graph. Remember, the question here is not to find the equation, but to graph it. So to graph it, I don't need to actually simplify anything, I can just use the slope and graph it and interpret it as a rise over run. Number 3. In this problem, we're given table of values, so we just need to figure out what exactly is asked of us. So we are asked to find the derivative of the inverse function and evaluate it at -2. And we know it's going to be the reciprocal of the derivative of the original function evaluated at the input that produces the output of -2. So this is how we know what goes where. Whatever input that produces -2 is what goes right in here. And looking at the definition of this function, it says f of 0 is equal to -2. So 0 goes over here. And since the derivative of the function at 0 is equal to 5, the answer is 1/5. It would be more challenging if they provided several values on the y-axis, like x equals 0, x equals 1, 2, and so on. Here it's pretty straightforward. All right, another one. Use the graph to estimate f inverse of 3. To estimate f inverse of 3, we're just gonna stick to the rule. The slope of the tangent line to the inverse at 3 is the reciprocal of the derivative of the original function at the input that produces the output 3. So whichever input gives you 3 is what goes right in there. Now, the output 3 for the original function is obtained when x equals 4. So the derivative of the inverse at 3 is the reciprocal of the derivative of the original function at 4. And according to the graph, that slope is equal to 0.5. So the answer is the reciprocal of that, which is 2. We have another similar problem, so I'm going to do it similarly. The derivative of the inverse at 2, it's the reciprocal of the derivative of the original function evaluated at the input that produces 2. So this is where the 2 came from, this is where this will go, and now we just need to figure out which input produces the output 2. So based on this function, the output 2 is produced when x is equal to 9. And the slope of the function of the tangent line to the graph of this function at 9 is 0.25, and the reciprocal of 0.25 is 4. So the answer is 4. All right, so we have a function which is a linear function, so it has an inverse, and we ask to find the derivative, and I'm going to show you both ways here. So one way is to to use the relation between the derivatives of the function and its inverse and say the derivative of the inverse evaluated at 4 is equal to the reciprocal of the derivative of the function evaluated at some value which is the corresponding input producing the output 4. So the question is now for which x the output is 4. So to find that, we need to solve this equation. So -1 is the answer. So now we're going to find the slope by taking the reciprocal of the derivative of this function, which is -3, and evaluating it at 1 means... Actually, we didn't even need this because it's a constant. I completely ignored the fact that it was a linear function. So the answer is -1/3. So method 2 will be to find f inverse of x first. Right? So we're going to completely ignore the relation and we're just going to pretend like it's not there. And we're going to find the inverse. And how do we find the inverse? We swap x and y. We're going to isolate y. And this is our inverse. Now we're going to find the derivative of this function. So we're just going to differentiate it. And we see how it's a constant. So the derivative evaluated at 4 is always going to be -1/3. Or rather, it's always going to be -1/3, regardless of whether the input is 4 or 5 or anything else. So that's the answer. And I showed you 2 different ways. And depending on the situation, depending on what's given, we may prefer one over another one. But in this lesson, we practice method 1. So same problem as before. To find the derivative of the inverse evaluated at 1, it's going to be the reciprocal of the derivative of the function evaluated at the value of the function that actually produces 1. So this will go here. Now we just need to figure out for which input the output is 1. And it looks like... interesting. At 8, the output is 1, so we need to evaluate the derivative of the function, which is the slope. And the slope is 0.148148, rounded to that is just 5. And it seems like this is just 1/7. So the answer is 7, approximately. Or I guess I need to do the math now. Why is it... we're looking for the reciprocal of 0.148. Oh my god. 148. So it's 148 over So this fraction can be, this decimal can be written as 148 over 999. And the answer is actually, 7 wasn't good enough. So it's 6.75. I'm glad I was given a second chance here. All right, for number 8, derivative of an inverse function at 1 is the reciprocal of the derivative of the original function evaluated at the value that gives you the output 1. So that's the only question here. At which input the output is 1. Looks like at 5. And it's going to be 1 over So same approach. So the derivative here will be the reciprocal of the derivative evaluated at some point, at the point corresponding to the point on the graph of the inverse function. So we need to know at which input the output is 8. But what's nice about the linear functions is that their derivatives are always the same. So regardless of what this value is, the derivative of the original function is always -5. So the derivative of its inverse is going to be always -1/5. So the derivative at -7 of the inverse, it's the reciprocal of the derivative of the original function at the point at which the function gives you -7. So we need to figure out what that value is, so we can just plug it in here. And according to this table, at -2, the function is equal to -7, which corresponds to the input of -7 of the inverse function. So according also to the same table, it's the derivative of the function at -2 is 2, so the final answer is 1/2. All right, so we have a function and we have to graph it. And to graph it, we may benefit from the setting up and finding the equation. And again, we're doing all of this for the inverse function, right? So this the point 3, -1 is on the inverse, on the graph of the inverse function. So here we have this, and the slope is the derivative of the inverse function evaluated at 3, which is the reciprocal of the derivative of the original function evaluated at -1. So we're going to look at we're actually not going to look at the graph because we actually need to find the derivative because the function is given to us by the equation. So first we're going to find the derivative of the function. And then we're going to evaluate it at -1. And now we know the slope. So the equation of the tangent line is y minus -1 is equal to 1/2 x minus 3. But to graph it, we don't need the entire equation. We just need to know the point, which is -1, 3. And rather, sorry, 3 -1, right? And the slope is 1/2, so it goes up 1 over 2. So that's the equation of the tangent line. This is the equation, and that's the graph of the tangent line. And we have another similar problem, meaning we will do it in a similar way. So the function is given. The point is given, so we're looking for the equation. This time we're actually looking for the equation, so we're gonna find it using the point slope formula. The point is given to us, and to find the slope we're gonna find the derivative of the inverse function evaluated at -2, which is the reciprocal of the original function, of the derivative of the original function evaluated at 1. So we're going to find the derivative of the original function, and we're going to evaluate it at 1. And now we got the equation. And we can isolate y. So it's -2/11 plus 1. So it's going to be plus 9/11. And before I input this, I would probably want to just double check. Just to understand what's going on here again. We have, here's my original function. Here's the point. It's going to be 1, -2. Here's the inverse. And here's the point on the inverse. Let's see if we've seen all that. A lot going on here. I guess this is not necessary. This is what we want. This is the definition of the function. So the red is the original function. The green is its inverse relation, I guess. And we're looking for the tangent line at this purple point. So this is my -2, 1 point. And the slope here is the reciprocal evaluated at 1. So we found it correctly. And the actual equation of the tangent line, let's see if it makes sense. And we see how this purple line totally passes through this purple point and does look like a tangent line. So that just gives us confidence that our answer is correct, because we fully understand what the problem was and we fully understand the solution. And this concludes this homework. If you have any questions on how to do calculus with inverse functions, please let me know.